Yeah, there needs to be momentum relaxed. Right. Hi everyone, I'm Patrick, and I want to talk about some symmetry-protected long-lived excitations in 2D electron fluids and their interesting dynamics. So I'm first going to talk about reviewing the normal picture of electron hydrodynamics, which has been very popular recently with the new very clean 2D systems that experimentalists have gotten really good at making. And there's been a lot of recent searches for hydrodynamics, but a lot of these searches are in 2D materials, and there are actually a lot of long-lived modes that we don't expect to be hydrodynamic except at very long length scales. And this was actually first noticed by Gurji in 1995, but it turns out this analysis of these modes is very subtle, and that's what me, Hao Yu Guo, and Andrei Shatov and Leonid Levitov worked very hard on, and we put out these 3 papers, and after a lot of confusion, I think we finally really understand what's going on, and that's what I'd like to tell you about today. So, as I said, in 2D, we expect there to be many soft modes that don't go hydrodynamic until very long length scales. And these modes have very interesting dynamics. They're kind of tomographic in that they really remember the direction they started moving in. And they also have an interesting subsequent angular relaxation that is very slow. And it's a super diffusive relaxation in that they move at small steps on the Fermi surface, but they violate the central limit theorem in an interesting way. And then finally, I'm going to talk about the influence on transport with new scale-dependent power laws that are different than hydrodynamic or ballistic transport. So, wait, one sec. Oh, this is the wrong slide. I'm sorry. Sorry. So the standard picture of Fermi liquid hydrodynamics is based on the Landau Fermi liquid lifetime. And standard arguments based on energy phase space, there's only a width of temperature around the Fermi surface, say that the scattering rate has to be slow in the sense that it scales as temperature squared. Now, keep in mind that this scaling is based on a restriction of energy phase space. And this derivation itself doesn't exclude other possible restrictions. And that's what's going to take place in 2D. But if we take this to be the collision rate and the relaxation rate of all excitations, then that leads to a conventional hierarchy of scales, where this collision rate determines a characteristic mean free path, and below this mean free path, electrons don't really collide with each other, and we get ballistic behavior. And above this mean free path, electrons will generically collide with each other, share momentum, and form a fluid. And we expect Navier-Stokes hydrodynamics to be valid at the longest length scales in the conventional picture. So in 2D, we actually get a new hierarchy of scales, where there's a new regime, which we call the tomographic regime, which is interaction dominated, but isn't conventional hydrodynamics. And all the dynamics in this tomographic regime are controlled by these new long-lived excitations. So at the smallest length scales, we of course, from Fermi liquid theory, expect that ballistic behavior is valid. But even at distances shorter than the conventional mean free path, this interaction dominated regime can actually onset. The precise crossover length between ballistic and tomographic is actually geometry dependent. And I'm happy to talk about that, but I don't have time in this talk. So, and over a wide range of length scales, we expect this interaction-dominated tomographic regime to happen. And only at the very longest length scales do these long-lived excitations finally have room to relax. And that occurs at this length scale on the left, called which I labeled Xi. And it goes as the mean free path times a factor temperature Fermi over temperature, which we expect to be a large number. And so only at distances much longer than the mean free path do we expect conventional hydrodynamics in 2D. So the origin of these new soft modes is determined from the fact that in 2 dimensions, it's actually very hard to scatter electrons by large angles. This is due to the many constraints and not much room to satisfy these constraints in 2D. In particular, momentum conservation keeps scattering on this kinematic circle in blue, and energy conservation together with Pauli blocking keeps the electrons on this red circle with temperature, which is the Fermi circle. And these circles only intersect at a small window, and that's where scattering can happen. But there's one exception to this, and that's head-on collisions where the circles coincide. And in these collisions, particles can scatter by large angles, and angular relaxation can happen, and current can move in different directions. But what's interesting about head-on collisions is they pull from opposite sides of the Fermi surface. And that means there's a large collection of modes that don't relax due to head-on collisions. And this large collection of modes we call odd parity modes because they're odd under inversion on the Fermi surface, which is precisely why head-on collisions don't relax them. Whereas even parity modes, which are even under inversion on the Fermi surface, head-on collisions are very good at relaxing them. So we expect to have a huge collection of long-lived excitations in 2D as opposed to 3D. So in 3D, we only expect to see current and density, which form the usual hydrodynamic modes that make up Navier-Stokes hydrodynamics. So a natural question is, why do we care? Like, we only really excite current with an electric field and measure current at the end of the day. So why do we care about all these long-lived modes if at the end of the day we only measure current? And the reason is that in any finite-sized system, these modes will actually be coupled to current. And we can see this by taking the Boltzmann transport picture with the collision operator that we diagonalize in the harmonic basis. And we Fourier transform this in both time, position, and Fermi surface angle. And we get a tight binding model in harmonic space. And this tight binding model has hoppings that are proportional to wave number. And so wave number actually couples all these harmonics together. And this is the reason that high harmonics matter, because they get coupled to current in any finite-sized system. So and notably we can show that the odd modes being odd modes being slowly relaxing is very important by just taking an extreme limit where they don't relax at all. And then we can construct this state here, which we can construct the state at any value of k. And this state will not relax at all, and it will carry current. And so therefore, if these odd modes don't relax at all, we have an infinite conductivity. So this says, A, that the odd modes are important, but also B, the precise relaxation mechanism of the odd modes is also very important. So in short, we expect that in this tomographic regime, these even modes are very short-lived, and these odd modes are long-lived, they dominate transport, but furthermore, we need to understand how they relax. So first, we want to create a description purely in terms of odd modes, and I've shown this here. We split the distribution function into even and odd parts, and we quote-unquote integrate out the even parts and form a description purely in terms of the odd parts. And we get this Boltzmann-like equation here, except notably the spatial term is squared as opposed to the normal Boltzmann transport. And that means that particles don't move directly ballistically. They actually diffuse back and forth. This is like a diffusion term, except it's only along the direction of the particle's velocity. So this tomographic regime has a 1D nature to it. Particles move back and forth. But furthermore, because it's an odd harmonic, when particles are moving backwards, they carry the opposite charge. This is precisely the definition of an odd harmonic. When you switch direction, you switch charge. So we call these particle hole switchbacks because it's switching from particles to holes. Now, the odd harmonic relaxation will gradually randomize the direction of these particle hole switchbacks. And that's a pretty subtle calculation that we spent a long time integrating the collision integral. But the end result is that we get the super diffusive relaxation where the relaxation goes as the partial theta to the fourth power. Now, you might expect some sort of diffusion-like behavior because we expect these odd harmonics to relax due to small angle collisions because that's the only thing that can happen. And head-on collisions don't affect them. Now, the reason it's not normal diffusion is that this is two particles collide at once. And it turns out that the collisions that matter most have very strong correlations between these particles. And that results in a violation of the central limit theorem and a super diffusive relaxation as opposed to normal diffusion. So to put it all together, we expect that the even harmonics relax at a constant rate. The odd harmonics will relax super diffusively. And we'll end up getting this quote-unquote odd harmonic master equation that will describe the transport in this tomographic regime. So from this odd harmonic equation, we can directly compute transport coefficients. So the conductivity in particular will have power laws that aren't present in ballistic or hydrodynamics. It'll scale linearly with temperature, and it'll have this width to the 5/3 power in a strip or a constriction of width W. And it's actually valid over a large range of length scales, from below the mean free path to above the mean free path, depending on the ratio of temperature to the Fermi temperature as shown here. We also really expect this transport to be very sensitive to a magnetic field. The characteristic cyclotron radius is actually much larger than both the width and of the system and the conventional mean free path of the system. And normally you wouldn't expect any influence of a magnetic field when the cyclotron radius is so large, but in this regime we see this. And we also see that the conductivity in this magneto-tomographic regime scales as magnetic field to the 1/3. So to summarize, this regime arises because head-on collisions dominate all angular relaxation, and that leaves out odd harmonic modes to dominate transport. These odd harmonic modes have this slow, super diffusive relaxation, and they result in scale-dependent transport coefficients that are different from ballistic and hydrodynamic transport. Moving forward, one thing I'm interested in is the fact that we have all these long-lived modes. At the nonlinear level, beyond linear response, one would expect them to be coupled together. And it would be interesting to see what sort of nonlinear effects you can see. Thank you. Yeah, Bert?
I just wondered if you suddenly introduced this width W.
Yeah.
But didn't talk about the geometry. This is like a pipe flow, you're saying, and instead of having a viscosity, this is something intermediate between a viscosity and something else. Is that what I'm supposed to understand there?
So you can compute an analog of viscosity. The viscosity will be non-local and will be related to this conductivity.
But it is flow through a pipe.
It's flow through a strip.
A long strip.
A long strip.
It's not a narrow, it's not a point constriction, but not like quantum point contact, but
so
rather a long strip.
Either one.
Either one would be the same?
Yeah. Yeah, what's important is that it's kind of long in one direction and short in another direction.
And W is the shortest?
Yeah.
Okay.
Thank you.
Very much.